Gonna do is not just write down the statement. I'll not just write down the statement because that would be pretty boring. What I'll do is give you an intuition of why the result is true, and then we'll see some applications of it. And there are many ways to apply the theorem, many different scenarios in which you can apply it. But my favorite is just add a bunch of conditions you like and hope that they all combine with the Chinese remainder theorem. So it's like you go for shopping and then you have to choose between two t-shirts that you really like. So instead of choosing, you buy both of them. That's what Chinese remainder theorem helps us do. So one key thing, so the intuition behind Chinese remainder theorem is that relatively prime numbers do not talk to each other. So do not talk to each other. So like you would see this phrase in a lot of math texts and used in an informal manner, and it often means something different in different contexts, but it's pretty intuitive. So something like if you have 7 and say 3. So this is also the essence of Bezout's theorem. Bezout's theorem. Oops. Which says that if A comma B are co-prime, implies that there exists x comma y such that ax plus by is equal to 1. So that is also based on the idea that they don't talk to each other. So for 7 comma 3, you would have 7 times 1 plus 3 times minus 2 equals 1. So the idea is if you look at them on the number line, and if you look at a step of length 7, if you look at steps of length 7, and if you have the same starting point and you look at steps of length 3, then eventually, since 7 and 3 are co-prime, the idea is that they will eventually meet, and they would meet at LCM of 7 comma 3, which is 21. So they would meet here at 21. This is the idea. But if the numbers are not co-prime, if you have something like 6 and then 3, what happens in that case is that if you start at the same point, then they would of course meet. Then they would meet. So for a step of 6, you just have 2 steps of 3. But if they start at different points, then you have a different story. A step of 6, and if you start at 1 instead of 0, and you take a step of length 3, you end up at 4, and then you end up at 7, and then you end up at 10, 13, and so on. And basically, this would be multiples of 6. So 6, then 12, this would be 12, and so on. So these two would never meet at one same point. And that is because the upper branch would be terms of the form 6k, and the lower ones would be terms of the form 1 plus 3k, 1 plus 3l. And these two can never be equal because 3 and 6 aren't co-prime. And that's the idea, because then 3 would have to divide 1. So that's a mathematical way to think of it, that if they were equal, then 3 would have to divide 1. But if you were to think about it intuitively, you could imagine a grasshopper hopping or whatever creature you like. And it's not very hard to see that 2 jumps of length 3 is basically 1 jump of length 6. So if they start at different points, they can never coincide. And this was because, well, this example is simple because 3 divides 6. But if you have something like 6 comma 9, then they have a common factor of 3 and one does not divide the other. Even in that case, 1 jump of length 6 is the twice of a 3 jump. And a jump of length 9 is the thrice of a 3 jump. So basically, if you start at different points, then they would never coincide. And mathematically, this is the same as saying the thing that they have a common factor of 3. So, but the idea is this. So if you have 2 co-prime integers, if you don't have co-prime integers, then you have an issue, because if they start at the same point, it's fine. Otherwise, it's an issue. But for coprime integers, if even if you start at different points, they will eventually meet. So, so if you start at say 0 for this, then you end up at 7, 14, and all. And even if you start at 1 and take a jump of length 3, they would still meet at one common point. And that's the whole idea of they don't talk to each other, because 3 is going to follow a completely different path and 7 is going to follow a completely different path, and those paths have coprime lengths which would eventually intersect because they don't talk to each other. So it's like you kind of get a feel for it after you were used to it, but um, it's this idea basically. You could once you start thinking of things like do not talk to each other, you would realize that what I'm saying is both the Chinese remainder theorem and also it's the Bezout theorem, because they both say the same thing. So you could use one to prove the other for this case. So this is roughly the intuition, and mathematically what I would write this as is, suppose you want an integer solution to the system of congruences. So one is x is congruent to say 0 mod 7 and x is congruent to 1 mod 3. So this is basically what I've drawn about. So what I said about this, they don't talk to each other, this basically corresponds to saying that this system would have a solution. So if you consider this, then this had the solution x congruent to 0 mod 21, which is what happened here. They both intersect at 21. And even this would have a solution, which would be some, and if you consider x congruent to 1, even this would have a solution x congruent to something mod 21. And now that's something you could kind of guess by just looking at the numbers 7, 14, 21, 28, and this would be what 1, 4, 7. So in fact 7 is a common point. So x congruent to 7 mod 21 would be a solution. Now, another thing is that this solution is unique. So firstly, there would be a solution mod 21, and then this solution would be unique, because if you try and put x congruent to k mod 21, so if x is congruent to k mod 21, that means 21 divides x minus k, and so 7 divides x minus k. And so x must be congruent to k mod 7 as well. And similarly, x would have to be congruent to k mod 3 as well. So one thing I could point out over here is that this is basically constructing and this is kind of like destructing. So yeah. So when you look at this, if you have something like x is congruent to 8 mod 21, if you assume that is a solution, x is congruent to 8 mod 21, that would not satisfy one of this or this. So you could test it, it's not very hard. But this is the essence of the Chinese remainder theorem. There is a solution and there's a unique solution modulo 21. So the general version of this would be something like the system x is congruent to say k1 mod l1, x is congruent to k2 mod l2, x is congruent to kn mod ln. This system has a unique solution mod L1, L2 till Ln. So the product, where we assume that they are all pairwise coprime. Now you could change it to the LCM of this, and there would be a few modifications, but let's just look at the simplest version. So this is assuming that L1, L2 till Ln are pairwise coprime. Now, so normally this is so what I just said about the LCM. That's one thing that I kind of discussed here. So in the case when the GCD is not one, when they aren't coprime, 6 and 3 aren't coprime, you could still have a common point, assuming the start is something suitable for a scenario. So in this case, a suitable start would be 0, a suitable start would be 3, 6, and over here a suitable start would be 0, 3, 6. So basically the GCD of this, because if it's a GCD, then this issue that we had about the GCD length jump not intersecting, that issue would be resolved if we start at a specific jumping point. So that would basically say that K1 and K2 also are divisible by the GCD. So if you have that case, then you can kind of do use the Chinese remainder theorem, even if L1, L2 aren't all pairwise coprime. But the gist of this is this thing. This has a unique solution. Another thing over here is that if you have something like, so this is kind of constructing. Now, if you have something like x is congruent to k mod L, and you have prime factors, and suppose these are all prime factors or any coprime factors of L, then you can break it down into x is congruent to k mod L1, then x is congruent to k mod L2, and so on. So you could break it down. So it works both ways. So this is the essence of the Chinese remainder theorem. And in some problems, you would need to construct an x. So what I said about just randomly adding conditions that we like, and just you hope that the Chinese remainder theorem assembles all of it together. That is this idea. And this idea is when you need to extract more information or when you need to split it down into prime factors, because modulo some random number isn't very helpful often. But if you have mod prime numbers, there are a lot of properties you can use. So this was the idea of the Chinese remainder theorem. So now we'll look into some problems, some application problems. So everything clear up to here? Does anyone have any doubts?
No.
What I'll do is I'll use my phone to join the call as well, so I can read the chat in case somebody posts a doubt. Yeah, the name on the phone is correct. Would this work for 2x congruent to 3 mod 7 and always x? So, like, if 2x is congruent to 3, then 2 has an inverse. So it's basically x is 3 times 2 inverse. So is that what you mean, or do you mean some system? If not pairwise coprime, can we substitute as mod LCM of all the numbers? Yeah, in that case, you can substitute as the LCM. But I think there would be some issues. Like there needn't always be a solution, if I'm not wrong. Just a second. Yeah, there doesn't have to be a solution. Like in this case, if you if you have something like x is congruent to 1 mod 3 and x is congruent to 0 mod 6, it's not so simple in that case. So what I basically said before, like in that case, if for the case of 2, suppose x is congruent to 1 mod 3, then then if it's something like x is congruent to 1 mod 6 or say 1 or 4 mod 6, in that case you would have a
Aditya, you're muted, I guess. Your tablet.
Aditya, you're muted.
Okay, can you guys hear me now?
Yeah, now you're audible.
Okay. I don't know how that happened. So what I'm saying is, if you have something like x is congruent to 1 mod 3 and x is congruent to 0 mod 6, then you have this issue that their jumps would never meet. So this doesn't have a solution. But if you look at something like this would indeed have a solution because one, if you have x is congruent to 1, then they both start at the same point. And if you have x is congruent to 4 over here, then the difference between 1 and 4 is 3, and 3 was the issue. So what would happen over here is, if you start at 1 and 4, so for a jump of length 6, if you start at 4, you go to 10, you go to 14, and for 3, if you start at 1, you will end up over here. You'll end up over here 3, then 7, um, then 7, then 10, then 13. So if you have something like x is congruent to say k mod a, x is congruent to L mod B, then if GCD of A comma B divides K minus L, then you would have a solution because like over here, the issue was that the jumps are of length 3. So if you start at two different points, you would have an issue unless those 2 points are congruent modulo 3. So if you start at 0 and 1, the jumps would never intersect. But if you start at 0 and 3, the jumps would indeed intersect because the jumps are length 3. And in that case, you basically what you generally okay, no, never mind. Yeah, so if K and L are congruent modulo the GCD, then we can do that. But in general, it's the simplest if all are pairwise coprime. Okay, so let's look at some example problems. So this is a classic example. So what I want from these examples is basically a discussion. So it shouldn't be something that I'm presenting. I would love if you guys can participate. So I've said the first two examples that I've chosen are that kind of a thing. Just add whatever conditions you like and combine them at the end. So stop worrying about everything. Just go for it all. So just that idea of buy all the t-shirts. So for this example, so let's see. The problem is that show for an integer c and a prime p, the congruence x raised to x congruent to c mod p has a solution. So something like show that x raised to x congruent to 2 mod 3 has a solution for x. Now, normally if you had something simple like some 3 raised to x, or if you had something like x squared, this would be solving a polynomial equation, this would be an exponential equation. And in modulo stuff, this would be related to primitive roots. So over here you can use like Fermat's little theorem. So 3 raised to p minus 1 is congruent to 1 modulo p. So over here, so you can control the exponent. So if this were a so if it were that kind of a problem, constant raised to x, then you could use Fermat's little theorem or you could use primitive roots and have some control. If you had something like this, then x square, then it's pretty simple because then you can just set x to be 1, 2, 3 or anything, and then quadratic residues or anything. So we want to kind of combine these two problems over here. So the key idea is that in x raised to x, the base moves modulo p and the exponent moves modulo p minus 1. Because after every p minus 1, it would start over because of Fermat's little theorem. So since GCD p and p minus 1 is 1, we consider the base and exponent individually and use the Chinese remainder theorem to combine. So this is the idea. So basically, 1 raised to x, then 2 raised to x. So if you just look at the base, then that moves modulo p. And after this, if you have p raised to x, which is basically 0, so you can write that over here, then p plus 1 raised to x would be this. P plus 2 raised to x would be this. So the base moves modulo p, and the exponent is something like, you could have some x raised to 0, x raised to 1, x squared. And once you have x raised to p minus 1, that is basically 1, which is x raised to 0. So x raised to p minus 2. Then x raised to p minus 1 is this. X raised to p minus, x raised to p minus 1 is this. X raised to p is this, and all that. So the exponent moves modulo p. Exponent moves modulo p minus 1, and the base moves modulo p. And because GCD p and p minus 1 is 1, we can deal with the exponent and the base individually and hope that we can combine them using the Chinese remainder theorem. So that's the idea. So is the question.
Why
Consider,
does
yeah.
why does GCD one implies we can work with them individually though?
Because then if we find, so what we want is x raised to x is congruent to c. So if we fix the base, then we can find the value of x such that this is congruent to c. And if we fix the power, I said the opposite thing, sorry. If we fix the power, then we can find a base for which one of these is c. And if we fix the base, then we can find one of this which is c modulo p, because that's a final goal. And so if you have one solution for this, so suppose you have that 2 raised to x is congruent to c mod p, then p plus 2 would also be a solution. 2p plus 2 would also be a solution. So the base would follow a congruency modulo p. And similarly for this problem, the exponent would follow a congruency modulo p minus 1. And since p and p minus 1 are co-prime, you can combine those congruences using the Chinese remainder theorem. So that's the idea. So this is the key idea, and now let's try and implement it. So is the question. Consider terms of the form n equals k raised to l, for which obvious pairs k comma l is n congruent to c mod p. So name any obvious pairs.
C comma 1.
And I'm sorry.
C comma 1.
C raised to 1. Did you say c raised to 1?
Yes.
Yeah. So c raised to 1 is one obvious pair. What about some other pairs?
C to the power p.
So one other pair would be c raised to p, because c raised to p is also congruent to c mod p by Fermat's-Riddle theorem. Yeah, c raised to basically anything of that form. So c raised to 2p minus 1 would also work. Then c raised to 3p minus 2 would also work, and so on. And you can also have something like p plus c raised to 1, then 2p plus c raised to 1, so on. And over here, p plus c raised to power p, 2p plus c raised to power p, and so on. So basically, we have these infinitely many pairs of k comma l. So the idea over here was to consider the base and exponent differently. And because the base moves modulo p, c, p plus c, 2 plus c, and the exponent moves modulo p minus 1, 1p, 2p minus 1, all those terms. Because p and p minus 1 don't talk to each other, hence the base and exponent move differently. So if you look at all the possible values, then you would have all these infinitely many possible values originating from this one common source. So one pair is c comma 1, and then you can basically find all the possible pairs. So any pair satisfying the base is congruent to c mod p and the exponent is congruent to 1 mod p minus 1. Any such pair would give us a valid answer. So for any such pair, we would have k raised to L is congruent to C mod P. So do you guys agree with this?
Yes.
So for any such pair, you would have k raised to L is congruent to C modulo P. Now in the original problem, so now let's move back to our original problem. Over there we had x raised to x is congruent to C mod P. So we basically want to set k and L to be equal. So so now we can finish and combine these using the Chinese remainder theorem. So what happens is we want to find some x, and we want to find x to be equal to k as well as x to be equal to L. So in the sense that x is congruent to C mod P and x is congruent to 1 mod P minus 1. So if some x satisfies both of these conditions, then because of this, you would have x raised to x is congruent to C mod P. And so this is our idea. So if we can find a solution to this system of equations, then we basically have solved a problem. We basically have found an x such that x raised to x is congruent to C mod P. And how do we know that this system has a solution?
By
Chinese remainder theorem.
Given.
Yeah, exactly. The Chinese remainder theorem, because P and P minus 1 are coprime. So this is the idea. This is the table that we make. So we basically, if we list all the possible all the possible numbers that we can think of, like the simplest ones that are congruent to C mod P, we observe that the base moves modulo P, the exponent moves modulo P minus 1. And so any number of the form k raised to L, which is C mod P, not must, but like it could satisfy this. And if it satisfies both of this, then it satisfies k raised to L congruent to C mod P. And if we want k and L to be equal, then we basically set that equal to some x and find a solution to the system. And we have a solution using the Chinese remainder theorem, and that solution works. Now, what this will give us actually is a solution modulo P times P minus 1. So we would have infinitely many x that work. But the beauty of the Chinese remainder theorem over here is that you don't know the value of x. So what we basically said is some abstract stuff that x must satisfy these two congruences and there would exist some x. Now I don't know what the value of x is. I just know that in this universe there would be some value of x that works, and that is the key idea of the Chinese remainder theorem. You do what you like, and then it's like kind of like magic. You'll certainly find a number that works. So this was the first problem. So was this problem clear? Does anyone have any questions?
It's clear.
Awesome. Now let's move to the next example. So this was from Russia 2018, and I really like this problem. So this question is, A and B are given positive integers. Prove that there are infinitely many positive integers n such that n raised to b plus 1 doesn't divide a raised to n plus 1. So A and B are say some 2 and 3 or say 2 and 7. Now we want to construct infinitely many positive integers n such that n raised to b plus 1 doesn't divide a raised to n plus 1. Now normally if you had something like divides, then you could do some congruency stuff, some hi-fi theorems you have. But this is doesn't divide, so it's very weird in that sense. So how would you approach this problem? There are many approaches, but let's see how many approaches you guys can think of. Just type down any rough ideas. Any idea is a good idea.
We can try like n to the power a plus 1 is congruent to k mod n to the power b plus 1, where k is not equal to 0. Like we can find some k for an
So could you repeat that? N raised to?
a plus 1.
Mm-hmm.
No, plus 1.
Okay, yeah. N raised to a plus 1.
Oh, wait, sorry, a to the power n plus 1. That
okay, a raised to n plus 1.
Congruent to
Mm-hmm.
k mod n to the power b plus 1, and where k is not equal to 0,
Yeah, that's a good idea. So if you have this, then that's a very good idea. So then if you have this, then n raised to b plus 1 wouldn't divide this. So, uh, okay, now let's see, any more ideas? Let's just gather a bunch of ideas, even if it's not related to the PPT, just for fun, because that's how maths should be done.
Maybe somehow show that there are only finitely many possible n such that it is actually reducible.
Okay, yeah, that's a good idea. So finitely many such n.
Can we choose a prime and then show that
Yeah.
it divides n to the b plus 1 and doesn't divide the other?
Okay, yeah, that's also a very good idea. Choose prime p that divides one, but not the other. That divides to say a raised to n plus 1, but not n raised to b plus 1. So in this case, if p divides this, but it doesn't divide this, then this can't divide this. Now, this is a very general statement, a very general statement. So in general, if this is not divisible by this, then you would have this. Now, one such scenario. So this is like this is a small subcase of this. This is a small subcase of this. This is the most general picture. So it's a good idea to start with the most general picture and then break it down into something special. So choose a prime p that divides a raised to n plus 1, but does not divide this term. Now, there are many advantages of this. One is that
It would be the other way around, right?
Yeah, it should be other way.
oh, sorry, yes, of course. P divides n raised to b plus 1, but not a raised to n plus 1. So if p divides this, but doesn't divide this, then this can't divide this. So this has many advantages. So this is actually the key idea for the approach that I have for this presentation. These are the advantages. Like if you have a prime p, now thinking of something like this breaks the problem down into two statements that are just simple divisibility. So one is that p divides this, which is a congruence where you can use some congruent stuff, and p does not divide this. That is again a raised to n plus 1 modulo p, and modulo p is always a good idea. So this is actually show finitely many such n is also a good idea. I don't remember exactly if it works, but something similar does work. So you can kind of use some analysis, some bounding. I saw a solution on AOPS, so AOPS, whatever. So this is Russia 2018. I think grade 10 problem 6. Grade 10 problem 6. So you could look it up over there. This idea kind of works. Okay, so for our purposes, let's look at this. So we want p does not divide a raised to n plus 1. This is the idea. P divides n raised to b plus 1 and p does not divide a raised to n plus 1. Now let's see how we can ensure these two conditions. So if we want p does not divide a raised to n plus 1, we want a raised to n to be something that isn't minus 1. So a raised to n is congruent to something modulo p. And over here, let's just take a step back and see. So we have to choose p and we have to choose n. So choose n. Yeah. So it's good to keep in mind what you have a control over. So over here you have a raised to n congruent to something modulo p. Now a is a constant. So n could be anything you like. So what would one condition on n what would be a condition you would place on n so that this is not minus 1, this is something else? How do you control a raised to n modulo p? How do you control 2 raised to n modulo p?
Probably p minus 1 times something plus 1.
Yeah, exactly. So to control exponents, the best way is Fermat's little theorem. So if you have say n is equal to say p minus 1, then a raised to n would be 1 modulo p. And 1 and minus 1 would be different, assuming p is not equal to 2. So let's just assume p is not equal to 2. So choose p. So one condition is p is greater than 2. And choose n. One condition is p minus 1 divides n. Okay. If you have these two conditions, then a raised to n plus 1 cannot be divisible by p. So that's this done. So that's this done. Now let's look at p divides n raised to b plus 1. How can we get n raised to b is congruent to minus 1 mod p? So over here we have control over the base. B is fixed. So how can we ensure this is minus 1 mod p?
We can take n to be a primitive root. Then for any b we will get minus 1, I guess.
Sorry, could you repeat that?
Or we can take n to be a primitive root.
I
Mod
think
p.
there's some issue with my net. I couldn't hear you properly.
I'll type it.
Sorry, still no clue. Could you maybe type it in the chat? Yeah, take n as a primitive root. Okay. So in this, when you have n raised to b is congruent to minus 1 mod p. So normally in this problem, what you would do, so suppose if you were solving this as a congruence, you would square both the sides mod p, and then you would look at the order. So the order of p would divide 2b and do stuff related to that. And so like if you know order, then this would imply that it also divides this GCD. So you basically what you want is order p to divide this GCD. So the idea of thinking about orders leads us to the idea of thinking about primitive roots. Because we have the freedom over the base, if we put n equals g raised to some l, where g is a primitive root, if g is a primitive root, then n raised to b would be g raised to lb, and we want g raised to lb to be minus 1 mod p. So g raised to what is minus 1 mod p if g is a primitive root?
P minus 1.
P minus 1 by 2. Yeah. So what we could do is set lb equals p minus 1 by 2 or l equals p minus 1 by 2b. So this is our idea. Set n equals p minus 1 over 2b. G raised to this. Set p minus 1 over 2b modulo p. Now over here we have two things. So this is one condition for g. Another condition over here is that p minus 1 should be divisible by 2b. Now p minus 1 is obviously divisible by 2, so we want it to be divisible by b. So we add that to our list of conditions. So we want 2b divides p minus 1, and we want n is congruent to g raised to that thing, mod p minus 1, whatever. So we have these conditions basically 1, 2, 3, and 4. So how do we combine these conditions? So we do this, and this is a typing error, it should be 2b. Now note that to ensure 2b divides p minus 1, we can just ensure b divides p minus 1.
Oh, here shouldn't it be 2b divides?
Yeah, it
Because
should be
b can
2b
be 2.
divides p minus 1. Okay, so at the end we have these conditions. So p is greater than 2, like we can just, that is one obvious condition we can add. So we basically have these conditions. N is congruent to g raised to this mod p. N is congruent to 0 mod p minus 1, and p is congruent to 1 modulo 2b. So we want to choose n and p, and if n and p satisfy all these conditions, then we are basically done. And now, come on guys, say the magic word.
So
CRT.
Yeah.
p can be chosen by Dirichlet.
So it's the Chinese remainder theorem. So you want n to satisfy this, and now this is kind of an isolated condition. So what you do over here is that you use Dirichlet's theorem And by this theorem, there are infinitely many primes that satisfy P is congruent to 1 mod 2B. And you choose any such prime because we don't want infinitely many, we just want one prime P. So you choose any one prime P. And once you have that prime P, you have these two systems and they have a solution by CRT, by the Chinese remainder theorem. And once you do this, you are done. So that's it. We have solved the problem. We have solved a problem 6 on the Russian exam, which is pretty cool, considering we only use the Chinese remainder theorem. So this was the idea. Again, the emphasis, what I want to lay my emphasis on is that you just add conditions you like. You just keep a list of the just keep a list of all the conditions you want, and hope that you can combine everything together at the end using the Chinese remainder theorem. So, any questions? Any doubts? Yeah, I did put this in the book because I really like this example. It's very instructive. So if there's any questions, feel free to stop me. Okay. So now, for now, I'm moving on. So let's see some more applications of the theorem, not just the add conditions you like type. So up to now, these two examples have been add conditions you like and just let the magic happen. That sounds weird, but okay. Let's look at some more examples that are slightly different, but they are cool applications of the theorem. So here's one example. This was, I don't know why I didn't write the sources. This was USAMO
2008.
2009. Problem 1. So prove that for each positive integer n, there are pairwise relatively prime integers k0 till kn, all strictly greater than 1, such that this thing is the product of two consecutive integers. So if you look at the problem, like you can't even smell Chinese remainder theorem being involved unless you start thinking a bit. So the key idea over here is we basically want this equation. So whenever you are stuck with words, whenever you're stuck with like is the product of two consecutive integers, you start thinking in terms of algebra. You start converting the English into maths. You start introducing variables. So let's do that. So we want this. We want a solution to this equation, kind of a solution. So in other words, we want to have x naught such that x naught square plus x naught plus 1 has at least n plus 1 prime factors. And over here, I want to point out something. The problem says are pairwise relatively prime integers k naught till kn. So now this is something I'm adding a condition. So what I'm saying is, suppose these are also prime numbers. So we basically just want to find n plus 1 prime numbers. Okay, this is USAMO 2008 one.
Yeah.
Okay, I'll fix that just a second. So instead of finding any relatively prime integers, we think about finding prime numbers. And if you think about it, this phrasing of any n plus 1 integers to n plus 1 prime numbers is actually equivalent. Because if you have n plus 1 relatively prime numbers, you would also have n plus 1 prime numbers, n plus 1 distinct prime numbers dividing this. So it's kind of an equivalent phrasing. But the idea is to change it into this. We want to find x naught so that x naught square plus x naught plus 1 has at least n plus 1 prime factors. So just changing this removes all the confusing stuff. So there's no k naught, k1, nothing. So now we just want to ensure that there's a certain number of prime factors dividing some x naught. So something like p naught, p1, this product divides x naught square plus x naught plus 1. So how do we start over here? So now solving the problem is far away. How do we start with these two weird expressions?
Split modulo each pi.
Exactly. Take modulo each pi. So what I said over here, construction and destruction. So if you have mod some weird number, it's often helpful to break it down into a bunch of congruences modulo the prime factors. So this is the idea of destruction. So Ivan has a handout on this, and he uses the terms construction and destruction, and I just like those terms. So to do this, you want a solution. You want a solution to this system. It's congruent to 0 mod P naught, then congruent to 0 mod P1 till mod Pn. So you want a system, you want a solution to this system. And now, because P naught till Pn, sorry, P naught till Pn can be any prime numbers that you have to choose. You just think about any one prime number P. So think about any one prime number P and just think about the question: what would P divides x squared plus x plus 1? What would P look like in this scenario? So you want to construct an X and you want to construct a P. So what would some P divide x squared plus x plus 1 look like in a general scenario? So
So this
once
is like,
yeah, you were saying?
yeah, so this is like the third cyclotomic polynomial, and so it's 3 or 1 mod 3.
Yeah, you could do that. This is the third cyclotomic polynomial, so it has prime factors. So this is the order theorem and stuff. So yeah, you can do that. But let's think of something simpler for now. So yeah, how do we know? So we basically want to know that the set of primes dividing x squared plus x plus 1 is infinite, because we want n plus 1 prime factors for any n. We basically want arbitrarily many prime factors of this x squared plus x plus 1. And once you have a solution, so what would happen is, suppose you get some x naught mod p naught. So you have this. You have x is congruent to x1 mod p1. Once you have this system, you can combine this and you would have x is congruent to some x mod the product. And this x would satisfy x squared plus x plus 1 is congruent to 0 mod the product P naught till Pn. So we basically want to find modulo each prime. Now show theorem. Okay. So what I said about using hi-fi theorems is a good thing, but let's think about something simpler. We basically want the set of primes dividing this to be infinite. Now, how do we find the set of primes dividing this polynomial? How do we prove that it is infinite? How do we prove that the number of prime factors dividing this expression is infinite?
In your book, f x f0 by f0.
Could you repeat that?
I mean, in your book, you use f of, I mean, p of x p not p0 by p0.
Okay, I'm sorry, but could you type that? I didn't get it.
Okay.
I think there's some issue with the audio. I can't hear you properly. Px p naught by p naught. Okay. Okay. So yeah, that is, so what he said is basically the idea involved in proving the theorem that polynomials have an infinite number of prime factors. That is the general idea. So yeah. That so that's the general proof. So over here, for this example, we can do something much simpler. So since we want to show that the set of primes dividing is infinite, so we want to show that the set of primes is infinite. Some set of primes is infinite. The one proof that we do know for doing that is Euclid's proof for showing that the number of primes in general is infinite. So, and that method is actually pretty useful in a lot of problems. So you should keep that in mind. So assume for the contrary that there are only finitely many primes that divide this expression p naught p1 till some pn. So we want to construct some x such that x square plus x plus 1 isn't divisible by pi for any of these I, because then there would have to be a different prime factor which is a contradiction. So this is exactly Euclid's proof. The construction he gave was p naught p1 till pn, the product, plus 1. So in this case also the same construction, a similar construction works. So if we set x to be equal to the product, then pi and x square plus x plus 1 are coprime for all I. Implies that none of these primes can divide x square plus x plus 1 if x is this. But it must have a prime factor because it is greater than 1, and so we have a contradiction. So this, we can use this method. Now, of course, you can use Shaw's theorem or you could use cyclotomic polynomials, but this is the simplest proof. And even Shaw's theorem is the proof of that is something similar to this, is based on this idea. So this idea of Euclid is very useful when you want to show the set of primes is infinite in some scenarios.
What's P naught, P1, Pn here?
P1, these are, so let me write it. Assume, on the contrary, that only finitely many primes divide x square plus x plus 1. By the way, x could be anything. So this is the set. This is the entire set. This is the infinite set. 1 square plus 1 plus 1, 2 square plus 2 plus 1, 3 square plus 3 plus 1. That infinite set. So assume on the contrary that only finitely many primes divide terms of the form x square plus x plus 1. And you say that they are these primes. Then you construct the number x to be the product. And what happens then is x square plus x plus 1 is coprime to each of these, because p naught p1, nothing can divide this. P naught till pn, nothing can divide x square plus x plus 1 if x is this product. So what that means is that this must have a new prime factor. This must have some prime factor, and it can't be one of these. That means there must be some other prime factor, which is a contradiction. So is this clear?
Yeah.
Yeah. Okay. So this is the idea. This was the idea. So we showed this, and because of this, we can pick infinitely many primes. So there are infinitely many primes that divide this polynomial. So you pick any n plus 1 of them, p naught p1 till pn. And for each p naught p1, there would be some x0. For p naught, there would be some x1. For p1, there would be some x1, and so on. And you can combine all of them using the Chinese remainder theorem to get one common x modulo p naught p1 till pn, the product. And that x would satisfy this. And this solves the problem. So in essence, it's just we break it down into primes. And once we have broken it down, it's just show that there are infinitely many primes, and we can do that using Euclid's method. So I hope this problem is clear, because this has two important ideas. If you have any doubts, again, you can just leave a message over there in the chat. So now let's look at one last example. This was APMO 2008. Sorry, USAMO 2008. This is APMO 2009. So prove that for any positive integer k, and this is the final example. So prove that for any positive integer k, there exists an arithmetic sequence a1 by b1, so basically k rational numbers, where ai comma bi are relatively prime positive integers, such that all these numbers are distinct. So basically, we want k rational numbers, k fractions in the reduced form, and all these are distinct, and this must be an arithmetic sequence. So now we have this weird looking problem of arithmetic sequences in rational numbers with distinct integers and relatively prime. So it's a lot of conditions. And so whenever you have a lot of conditions, you look at them step by step, you look at them one at a time. So any ideas how we would start this problem?
We can try finding a particular common difference which would work,
Yeah,
and
that's
then
one thing.
finding initial AIBI for that difference.
Yeah, we could try finding a common difference, D. So we could find D. I'm not sure if this will just trivializes this. Like, how is it related? Dirichlet involves an AP sequence of integers with prime factors dividing them. Over here, you don't want terms dividing these, so they don't have to be related in that sense. So one idea you could start is ignore the distinct part. So look at the problem one step at a time. So name one obvious sequence of rationals in an AP. So the key condition of this problem is, of course, to find an AP sequence of rational numbers. So let's start over there. Name one obvious sequence of rational numbers that are in arithmetic progression.
So keep the denominator fixed and take the numerators in AP.
Yeah, that's right.
Denominators are all one and numerators which are in PJ just an AP.
Yeah. So you could choose any arithmetic sequence of integers, and so one obvious sequence is just an arithmetic sequence of integers. So a plus d till some a plus n minus 1d. One AP, if you want rational numbers, one AP would be a by 2, a plus d by 2, and so on. Then you could have a third of these, a fourth of these, whatever. So a general AP series would look like this. So let's start over here. Now we have an AP sequence of rational numbers, but what we want is, now let's look at the second condition. The second condition is that ai comma bi are relatively prime positive integers. And to ensure relatively prime integers, what we do is, so if you have a rational number and you want the numerator and denominator to be relatively prime, you basically just are talking about canceling the common factors. So if this is something like 4 by 6, you write it as 2 by 3. If this is something like as 8 by say what 18, you just write it as 4 by 9. So the relatively prime part isn't that hard as well. You can just cancel out the common factors. The hard part now is that after canceling out, the terms that you have must all have distinct numerators, distinct denominators, and basically any two numbers must be distinct. So for that, you must have a control on what this fraction simplifies to. If you can't control what this simplifies to, you can't talk about the number you have after that, which must be distinct, different from the other ones. So you must have a control on what factor cancels out. So over here you cancel out the factor 2, and over here you cancel out the factor 2. So how would you control what happens? How do you control what cancels out? So let's say if you have the sequence a by n, a plus d by n, a plus 2d by n, and so on. So let's say a plus n minus 1 d by n. And by the way, as before, let's just list down. We can choose a, we can choose d, and we can choose n. So let's say the common factor over here is some prime p naught. Over here, say some prime p1. Over here, it's a prime p2. Over here, it's a prime p3. Then you would cancel out these fractions. Sorry, you would simplify these fractions by canceling the factor p1 from the numerator denominator. You would cancel out p2 over here, and the remaining thing you would want the numerator and denominator to be relatively prime. So what you want is that the only common factor between a and n is p1. So you want the GCD of a comma. You want the GCD of a comma n to be p1. You want the GCD of a plus d comma n to be p2. So this says two things. One thing this says is that p1 divides both of this. The second thing it says is that p1 is the only number that divides a and n. So over here as well, p2 divides both of this, and p2 is the only number that divides both of them. And if we cancel out the common factors, the denominators are no longer equal. So that's one more plus point. So how do we go about doing this? So we want prime numbers p1. So we also choose p1 till pn. So how do we go about doing this? How do we choose prime numbers such that the GCD of this is p1, GCD of this is p2? How do we do that?
I have a vague idea, shall I say?
Yeah, sure.
We can take n as like p1, p2, so on till pn. And
Okay.
then we can pick a as, let's say, p1 into pn plus 1. And then a plus d as p2 into pn plus 2, and ensuring that they come in AP. But ensuring that is
You mean something like this?
p yeah,
P,
into some other prime, which is not
okay.
among these n primes.
Okay. You mean this?
Yeah.
Yeah, that's one good idea. That's a good idea. And you could have a plus d equals p2 times some pn plus 2. And what that would ensure is that the numerators are all distinct. That would also ensure the denominators are distinct. And all those would be co-prime. So that's a nice idea. So one thing we want in this idea, so is that p1 divides a. So firstly, suppose we choose any primes p. So for now, let's say we have chosen the right primes. So God gave us the right primes. Now p1 divides a. We want p2 divides a plus d. So while this idea would work, you do want this condition. So let's just look at how we deal with this condition. p3 divides a plus 2d, and so on. So so you basically have this system. So you want this system. So suppose we pick n equals p1 till pk or pn, whatever. You want a common to 0 mod p1, a plus d, and you have this system. Now, how do we ensure this has a solution?
We choose all the pi to be much bigger than like k, and then we choose d to be 1 by k minus 1 mod pk.
Okay, yeah.
And a to be 1 mod p2 up to pn and 0 mod p1.
So you choose a to be 0 mod p1. Okay, so you choose this to be 0 mod p1.
And all the others is 1, and then just solve for d separately.
Okay, yeah, that definitely works. So you could choose a to be 0 over here, and over here you choose a to be 1, and you have the system 1 plus d, and so on, till 1 plus n minus 1 d. And then you have a system, and you have a solution by the Chinese remainder theorem, by the CRT. So yeah, this definitely works, but something simpler we could do is, instead of choosing A to be 1, we choose A to be the main subject. So A is congruent to 0, A is congruent to minus D, A is congruent to minus and minus 1D. And let's say there is some D, then this would give us a solution. A is congruent to something mod a big number mod n. And over here we want so yeah, even this works. So over here you would choose D, over here you choose A, but let's just choose A. There's something in the chat. Okay, that's a different idea, so we can look into that. But for now, let's just continue with this. So we have the system, we would have a solution, A is congruent to something mod n. So this ensures that P1 cancels out in the first fraction, P2 cancels out in the second fraction, and so on. The second thing we want is that Pi is the only common prime factor between Ai, comma n. So suppose so we have P1 divides A. Suppose P1 divides A plus 3D. Is this possible? Like, is this even possible? What would happen is this would imply P1 divides 3D. How can we ensure that this does not happen?
We can pick like P1 to be very greater than n, like the smallest prime as greater than.
Yeah.
And we can pick like D, we can pick ourselves. So we can pick such a D which is co-prime to all the primes we chose.
Yeah, exactly. So that's a nice idea. So in general, if Pi would divide A plus I minus 1D, Pj divides A plus J minus 1D. So this would imply, Pi only divides this. This would imply Pi divides J minus ID. Now we have complete control over D. So let's just choose the simplest thing. Let's choose D equals 1. Or you could choose something like D which is co-prime to all those prime numbers. And now, if you don't want Pi divides J minus I, you could choose Pi to be greater than J minus I. And since J minus I is the difference between any two terms, you could pick the prime Pi to be greater than n. So let's get back here. So choose D. So we choose it to be 1. And then we have chosen this as well, to Pn. Now choose all this. So the only condition over here is that all these are greater than n. So greater than n, we can choose any prime, any n primes we like. And we have a condition by CRT. We have a value of A by CRT. So we are almost done with the problem. So let's just trace our steps. We found an arithmetic sequence. We found an AP. We simplified by cancelling out the prime factors. After cancelling out, the denominators would be different because they were all the same initially. But after cancelling out, denominators would be different. The numerators would be A by P1, A plus D by P2. And we know P1 divides this, P2 divides this. So we can indeed cancel that factor out. And to ensure they are distinct, we haven't gotten to that part yet, but we did get to why P1 is the only common factor, because P2 cannot divide A, P3 cannot divide A or anything because of this condition, D equals 1 and these primes are greater than n. So we have almost solved the problem. The only thing we have to deal with now is that all the numerators are different, all the numerators are distinct, and no numerator can equal a denominator. And that condition is something I leave to you guys. It's your task, and it's not very hard. So Bj this is basically n by Pj. So you just simplify these two equations and show it's not possible. And that's it. Yeah, CRT gives so much flexibility to work on. So that's it. We are done with this problem. And this is an APMO problem, and it's a good question. So what we did is, if I were to summarize, We chose an AP. We chose the simplest possible AP with common denominators. We chose prime factors for each term that we would cancel out. And we chose the prime factors in such a way that the numerator only is divisible by that prime factor. So you could say something like that. The only thing is we didn't even have to think of Pn plus 1. This would be anything that is not that is different from all the other primes. So it is divisible by P1 and the remaining part is something co-prime to the other primes. So that is one thing we did. And to ensure everything was distinct, that is just simple algebra. And that's it. We are done with the problem. Any questions on this one? Yeah, this was it a P4? Oh, wow, nice. So any questions on this problem? Any doubts? Okay, so that was the last example I had. Now before ending, let me just give you guys a problem to think about. So it came in Putnam this year, and it kind of involves some ideas I talked about. So let me just pull it up just a second. Oh, by the way, Happy New Year, guys. I totally forgot about that.
Happy New Year. Yeah.
So this was an A5. So yeah, it's supposed to be pretty hard. So let A be the set of all integers n such that n and 2021 are coprime, and of course it's 2021 for every non-negative integer j, oops, integer j, let s of j be the expression, be this expression where n is in the set A. So determine yeah, so this is the question. What is the correct way of pronouncing Putnam? I think it's Putnam, but it's Putnam, so you don't know anything. Could be anything. Could be Putnam. So this is the question. You basically have this expression is the set of all integers which are less than 2021 and coprime to it. And for every non-negative integer j, you define the expression s of j to be the sum of n raised to j, where n goes over all those numbers. And you have to determine all values of j such that 2021 divides s of j. Now this involves some ideas from our class today. This does involve some more results in number theory. So what you could do is you could message me on WhatsApp or you could message me on AOPS asking for hints on this problem if you want to try it. It's actually a good question. It's not a bad question. So you could do that. And this is your final homework, some food for thought. Hopefully you guys enjoyed my session today. Now, if you have any questions, you could ask me. Yeah, this isn't as free as you would expect from a construction type problem because this isn't that. It's very rigid in that sense. My AOPS ID, I'll put it on the chat. Yeah, it's Wizard32. I'll also put my WhatsApp number in the chat if you guys want to message me over there because I responded the fastest over there. Yeah, so if you want to try this problem, if you need any hints, you could message me. I could help you out. Do try this problem out. It's actually nice. It's kind of cute, and it's an A5. So the pride you would have after solving an A5 would be amazing, and you can boast about it. Okay, so if you guys have any questions or want to talk about anything in general, I'm going to be here for the next 10 minutes. But thank you so much to everyone who attended this class because it was really fun. It was an amazing opportunity to be able to talk in this club, this amazing club. I looked into it and it's pretty good. Something I definitely want to be a part of.
I
So
mean,
thanks everyone for attending.
thank you so much for coming. This is an amazing class, amazingly well taught. So thank you so much for that.
The pleasure is mine.
Thank you so much. Yeah.
Yeah, Rohan has written a very good handout on polynomials. I'll be here for the next 5 minutes. So if you guys have any questions, you can just ask. And otherwise, you're free to leave if you want. Go have dinner, go on a drive, whatever.